I'm Peter Bindels from TomTom International, and I'm here with the presentation on the million-line project. The first question that comes to my mind is, when I read this, a million-line project, what does that mean? What does it actually mean? When is it a million-line project? I mean, I can come up with a simple example. Is that the kind of project that we're talking about? Actually, it doesn't do the things that million-line projects have as their difficulty, which is that they are hard to understand. This one's really easy to understand. It's actually so easy you could turn it into a for loop of 5 lines. But that's not the problem that I'm going to tackle. I am tackling the one with projects that have a really long runtime, that have a really long lead time, that have been worked on for 20 years, that have had hundreds of developers, and many of which don't work here anymore. Most of the people that are working on it now haven't seen most of the code. In fact, some of the code hasn't been seen in 10 years, but it's probably still used. It's had a lot of time to build up technical depth. So, given that kind of problem, how bad can it get? So we found a bunch of things. We looked at, for example, how many headers we have. We have about 2,600 headers that if you include one of them, your code will expand to at least 100,000 lines of code before compiling, not including platform SCL. I'm here with the presentation on the million-line project. The first question that comes to my mind is, when I read this, a million-line project, what does that mean? What does it actually mean? When is it a million-line project? I mean, I can come up with a simple example. Is that the kind of project that we're talking about? Actually, it doesn't do the things that million-line projects have as their difficulty, which is that they are hard to understand. This one's really easy to understand. It's actually so easy you could turn it into a for loop of 5 lines. But that's not the problem that I'm going to tackle. I am tackling the one with projects that have a really long runtime, that have a really long lead time, that have been worked on for 20 years, that have had hundreds of developers, and many of which don't work here anymore. Most of the people that are working on it now haven't seen most of the code. In fact, some of the code hasn't been seen in 10 years, but it's probably still used. It's had a lot of time to build technical depth. So, given that kind of problem, how bad can it get? So we found a bunch of things. We looked at, for example, how many headers we have. We have about 2,600 headers that if you include one of them, your code will expand to at least 100,000 lines of code before compiling, not including platform and SCL. So that means that on average, every file that we compile will have at least 100,000 lines of code and probably more like 1 million or a few million. There are a lot of stale dependencies. You're specifying in your code which things you're including, which things you're using. You're also specifying it in build files. And in the build files, if you have a mistake, and if somebody else includes it for you, you omitted it, it's not going to notice. Which means that somebody else can then depend on you and transitively get the same dependency and not actually depend on you, but still need that dependency. So you get essentially a sort of escalation of technical debt. You get the problems that you had when you started, and you have a more amplified form of technical debt that even if you try to remove it, you just can't get rid of. So that's the kind of problem that I'm going to tackle. Let's skip that one. So there's a solution to that, which is one that HR and management like, which is we make the developers write documentation. We make them write a whole lot more information. We let them clean up the code so that people can understand it a little bit, but not too much because it costs money. We try to keep people on board because then people have been there for longer. They might be a bit unhappy about it, but they'll be there for longer. We have standard ways of doing things. We try to enforce a standard way of doing things. We have code reviews. Let's get all the senior people that actually did know how to make software and that do know the system, let's make them do code reviews instead, so that the new people can write the code and they can do code reviews. Let's make all the senior people architects and designers, so that they can at least ensure that everything's coherent. This doesn't work. Mostly because when you have 7 million lines of code, and I'm assuming a reasonable amount of time of people being in a company of like 3 or 2.5 years, the people that have been there for 2.5 years, given 7 million lines of code, if you do a bit of math, that's about 2.5 seconds per line of code. Assuming that you never do any work, but you're just reading the code. So that means that on average, you can assume that anybody in the company has 90% chance of never having seen your code and having no idea what it is. So there's a way to deal with that, which is what many people do. That's fine. I can live with that. I don't understand this code. I've never seen it before. I don't know what half the stuff does. There are many people that will do this. They don't explicitly say it to you, but they will be just using your code, using interfaces they don't understand, things they've never seen before, things they don't even look up, just because it's impractical to just go and look everything up. But there's more important things you could do. There's better things. I mean, you wouldn't be here if you didn't care about the quality of your code. So I don't think any of you would try to do this, at least not intentionally. So for starters, first realize that it's not just you. This is the entire team that works on the navigation engine. So not even the entire product that we make, just the navigation stuff. And that's a pretty large group of people. And on average, half of them have been at the company for 2.5 years or less. So half of that group, say everybody around the car, they all don't know about it. There's a half of the group, they do know about it. They have been there for a long time. You can ask them. You can talk to them. You can go to them and ask them, you've made this. How does it work? Where did it come from? Why did you make it like this? There's a second thing you can do. You can just take the code base you don't understand a thing about. Go in, find out the thing you want to change, and go and change it. Run the compile on it, run the unit tests on it if you have them. I'm assuming that you do testing. And figure out why it's a bad idea, why it doesn't work. There's a bad thing in the code. I don't understand why it's there. I asked 3 people, they don't understand. It's probably legacy. The guy who did understand, according to the version control, he doesn't work here. He didn't work here since 2000. I'm just going to change it. I'll just try it out. Remove this function that I think does nothing. Compile. Yeah, it is used. Actually, nothing works now. Let's put it back. I learned. So now I understand. When somebody now comes to me with a question like, why do we have this function that's called serials with Z at the end? What does it do? But you can explain it to them now, because you know. And one more thing that you can learn from it is that actually code is not something you should treasure. Code is a cost. What is there? Does anybody know what it does? It's a very, very well-known function. The only thing I changed about it is the name. It is the inverse square root. The thing is, if you need this, somebody's going to read the code. Somebody's going to have to figure out what does it do? Why is it here? Why don't we use some other library that does it for us? Why don't we have a name that's clear to me? The more code you have, the more of those questions you'll have. So every time you have an opportunity to take some code and just remove it entirely, you have 3 XML libraries. Maybe you can just use 1 or maybe 2. That saves in mental load for everybody who's reading your code. And also saves in the amount of time for making something new. I need to read an XML file. What do I use? Use the library, or, well, we have 3 options, and these guys like this. And no, just simple. Get rid of all the duplication you have. I'm also assuming that you're going to be doing a lot of testing. And testing is a thing that management likes a lot. And they like it a lot because it makes a number. And the number means quality. If it's low, it's bad. If it's high, it's good. But actually figure out what test coverage means. This test coverage only means that this code was actually used to run these tests. It doesn't say these tests are things we want, or these tests are correct in what they're doing, or all the other code is useless and we don't want it anymore. It only says that this code was used for the test. So when you look at test coverage, figure out this stuff that we covered. And we have an excellent example of that. We had one, at least, which was a perfectly tested class. It did its function correctly. It had a clear interface. It had good test cases. It had a really excellent runtime. The unit test ran in no time at all. It was excellent and completely unused. And looking back, it had been in use for 3 years. So it'd been running just a lot of stuff, and people had been looking at the code thinking it was in use somewhere, modifying it in places, but it didn't do anything. And the biggest one is figuring out tools. Now, most people, when they first use a compiler, they're like, I type in the code that's from a book, and the compiler tells me I made a mistake. I didn't understand it, because I just knew the language. And it tells me I made a mistake. I'm not happy about that. Let's turn off the warnings and just keep on the errors, because, well, I have no choice. Just keep on the errors, make it run, and it crashes. Because actually the thing it was warning about may have actually been wrong. Or maybe the warning didn't apply in your case, or it was somehow still okay despite that. But as you get further, you figure out that actually the warnings that it gives you, is it helping you that you have something here that is probably wrong. Depending on the warning level, it's either 100% wrong, or nearly always wrong, or for nearly everybody, this is avoidable, but it could be fine for you. So use the tools as much as you can. So there's a GCC and LLVM. You're using it anyway. You already have that in your build setup. Turn the warnings to the maximum, get their information, even if you're just ignoring it for now. Figure out when you have a bug in some code, what warnings are on there. Let's look at that first. It's probably wrong. There's also a thing about warnings that they give you value, but they also take time. In case of the compiler, well, you're spending the time anyway, because you kind of need to build it to test it. In the case of a Coverity or PVS Studio, it can take a lot of time. In the case of Valgrind, I've had a case where I didn't want to use Valgrind anymore because my test took 15 minutes, and it had a crash at the end. And I figured, well, running in a Valgrind will get me the exact result of why it crashed, but it will also take 15 minutes times out a factor of 100 is a week. I can solve that faster than that. So I like my tools to be very fast. So given all these things so far, you're probably in a reasonable situation. You know somewhat how it's met together. But the people that are coming after you, they still have no idea. Somebody else is going to join your company in probably next Monday. How is he going to figure it out? So the thing you should be doing now is to make it better. So very simply, if there's code, you need to read it. If there's less code, I don't need to read the code. So if I have a bit of custom code, I have my own string class, or I have like 26 different string classes due to legacy reasons, and I can replace it with one string class, or maybe 3. That already saves a lot of people a lot of figuring out why it's there, what is it doing there, why did it end up here, how do I convert from A to B to C to D. Remove the libraries you don't need, find and kill the dead code and dead headers. And you would be surprised how many projects actually have dead headers but don't even realize that they do. And the final one is to test. I've called it requirements. I want to call it functions, or the functional things that your product does, but well, for functions we have a different concept in mind, so it doesn't fit. So the things that your product should be doing, make tests for that, get them to run. And then figure out, well, this is the stuff that my product should be doing. I am doing a navigation, I'm planning a route, and all the route code is touched. That's good. All this other code is not touched. Why do we have this? Why do we have a color scheme in the routing engine? Let's try to figure out if we can get rid of that. Speaking of navigation, you should have code that you can navigate through. At any point in time, when you have a bit of code, you have it on your screen, you should know where in my code base could this be. If it's doing some routing logic, it should be in the routing engine. If it's doing something that is not routing, it shouldn't be in the routing folder. You should have readable code. I'm not even sure why I need to mention this, but I'm pretty sure I do because I've seen too many examples of people not doing it. People will be reading your code. Your compiler also reads your code, but people will be spending disproportionately more time on it. They will be spending days, maybe weeks on it, per person looking at it. And assuming you have code reviews, people already have to spend a lot of time on it, even if they don't want to touch your code. So make your code very readable. And make it stable. And stable is a difficult one. You can make some bit of software that is of itself stable, and yet doesn't have the ability to function in a stable system. For that, you need to think about components. If I have a component that has a header with a certain name, and I call it, say, engine, because it's the engine of my component. Now somebody else wants to use my base component, which includes the engine. If he also has his own engine, well, you can get one of them. But you're not sure which one. So with stable code, I actually mean your code should be in such a way that even with people modifying it, people looking at it, people using it, people not using it anymore, it should keep functioning as is. The big one is don't repeat yourself. If you have a small project and you have a bit of repetition, you have a configuration clause and you duplicate things 3 times, that's probably okay. The worst thing that could happen is you have a bit of code duplication in one file, you'll find that. Doesn't matter. If you have a big project, you have a little bit of code duplication here, a little bit there. People don't know which one to use, so they make an abstraction function on top of it, which takes one of these 2 as possible input. Then somebody takes that, makes it into a template function that calls into that function, except in this one corner case that we want to hook. And in the end, there's no way to get rid of that again, only because you started with a bit of code duplication. So get rid of duplicates wherever you can. Try not to mention anything more than once. So C++ is already great for that because we have a constructor that we need to put somewhere, we have a destructor. If you've constructed it, it's on the stack, it will get destructed at some place, but there's nothing to put there, it happens automatically. So we can't forget that, compared to, say, Java, file open and file close. Your component should be very small. And the word small is the wrong meaning that you get in your mind with it. If I compare these, I have a hammer, and a hammer is physically kind of big, and I have a Swiss Army knife. The Swiss Army knife is made to be taken on. But if I look at how small these things are, I have a handle and a head. I have only 2 things. There's only one thing that I could be doing with it, and if I'm using it wrong, I will figure it out very fast, because it doesn't work. If I have a Swiss Army knife, I could be doing 10 different things. I can't use them at the same time. There's all sorts of implicit contracts in that. So the one on the left is a lot bigger component in far as I am mentally perceiving than the one on the right. And this should be easy to use. If you have a single button, I know how to use that. I don't know what it does. You probably need to put a sticker next to it. But I know how to use that thing. That's it. I initially had a picture next to it of the ADVAC computer, which is a really computer, it's like 50 years old. And it came with a bunch of racks and a whole lot of dials and buttons and things to do. And you needed to understand most of them to use the device. It's basically a computer like the ones we have now, but it's way more complicated to use. But it does the same thing in the end that this does. I have a computation, I want to have some result. I have a result. On the old one, I'm spending way more time, I have a way more complicated interface, I spend a lot more time figuring out and remembering how to use it before I get to that point. So even if I did this, I get the result, I walk away. But in this case, I walk away with just a mental load of, here's my product, I'm happy. In the other case, I'm walking away with a giant mental load about this button does that, and that button does that, and if I use these buttons together, it will probably wreck the machine, so I shouldn't do that. Bad idea. So given that you have a component, it has some responsibilities. It has some things that it should be doing. But people don't write it down. It's always the why is the component here? What is it for? What does it do? How does it do it? You shouldn't want to ask the question, but people will do. So to find that out, talk to your colleagues, read the documentation. And in worst case, just, well, this component is called routing engine. Keeping my fingers crossed here, but I'm guessing this is a routing engine. No certainties. If you don't have that, you can figure it out from dependencies. And dependencies are a really nice thing to have. You have a component, it uses some other component. And I do that with an include. I include some header from it, which allows me to instantiate the class as defined there. I also tell the compiler, because it needs to be able to map my include statement to the right include file. And I tell the other build tools, I tell the code analysis tools. There's a word on this slide that I don't like. When I say I don't repeat myself, why do I repeat myself? Can we do something about that? Can we just not do that? I mean, I have include statements. I have an include from file A to file B. So there will be a dependency from component A to component B. I just do that 7 million times automatically. Why not? I mean, how hard can it be? Okay. So let's start there. We start from TomTom codebase. It's 7 million lines of code. It has like 500 components, roughly. And there's a lot of test coverage. And that makes it very nice, because that means that every time we do change something, we can figure out what it's broken and what things still work. I'm running this on a reasonable laptop, as in it's not the best of the line, but it's not bad. And I think I should be able to match the C preprocessor. So, I mean, tools should be fast. This is going to be a tool, 2 seconds. If it's more than 2 seconds, I've lost my train of thought. So let's try it again. Number one, let's see if it works. I hack together a bunch of shell scripts, read all the code, and that works. It gets the result that I get. It shows me the information I wanted. It shows me the dependencies we have. But it takes 2 hours to run. I mean, it's no C++. So taking that to cycles per line of code, that means I'm spending 3 million cycles per line of code. Well, this is just too slow to be usable. So let's try it again. 1.5. Let's extract the function that I think, because I can't profile shell script, I think is slowest, and let's extract that into a C function. And that helps. It's now running in 20 minutes. That's good. 20 minutes is good enough for me doing an occasional analysis, but it's still 20 minutes. I don't want to wait 20 minutes. And in particular, we find out that this thing can find cycles in our dependencies. And the cycles, I will get to that later, are a really bad thing. So we want to put this in the infrastructure, in the build infrastructure, so that every time we check something in, we check, did we make it worse? If so, fail the build immediately and don't even allow them to figure out if they fix their own problem. So we start it again. Number two, we do it in Python. Yeah, it's almost the wrong conference for this. I'll get to that. So we make it fast enough for CI use. We can integrate it into the build system. It takes 5 minutes. The rest of the build takes 15 minutes. Average incremental code's 20 minutes. It's a reasonable percentage of that. Yeah, 5 minutes. I want to use it more. I want to do more with it, but I can't because it's still too slow. So I figured, well, yeah. So I did it in C++. Finally. So it should be fast enough for interactive use. I want to just push the button, get a result. Change parameters, get a new result. And preferably without caching, so it can get out. The caching can get stale, then you need to update the cache, then you have all sorts of other problems. I don't want to add a cache unless I must. So let's just try not to. I mean, my computer is really fast. It runs at 3 gigahertz, times 4 cores, it's 12 billion cycles of processing power. It has enough memory to hold everything in memory, including my own DNA, times 50. It should be able to do this. So we add some interactive queries. We add some information you can get from it. So the component that I have, what things does it have, what files are in there. It's quite a lot faster, 5 seconds. Can we go faster? Of course we can. So put Valgrind on it, find out what's causing slowdowns. It's completely not what I expected, as always with optimizing. So now it runs in 2 seconds. We add a bunch more commands. We add the ability to take whatever it detects about a dependency or about a component and take all the files that are in component, all the include statements, the include paths that somebody else will need to access my files, the link libraries, the targets that I'm depending on. We'll just put that in a CMake list. No idea if it will work. We'll just, fingers crossed, to see if it works. And then I figured, well, in an evening, let's just see how fast we can make this. And then it ran in 1.1 second. That's fast. It also kind of broke the line of code counting, because it tries to find out how many lines of code are in a file, so it can tell you how big your component is. But it was optimized so much that first thing it did was try to skip most of your file if there's no hash in it, because then it couldn't be an include statement. So I can't tell you how much lines of code your component has, because I literally didn't even look at it. So let's turn that off again, get back to the 2 seconds. It's fast enough. So what can it tell you? It can tell you your public interface. So given I have a component, there's a bunch of headers there. We separate out an interface and implementation. It can tell you which of those files and interface are actually on your interface, and which files and implementation are actually also in the interface, but just in the wrong folder. It can also tell you which dependencies do you have. You have a dependency on this other component. Is that a dependency that I need to tell people that are using my component that also need to depend on it? Because if you don't need to depend on it, you get a smaller dependency tree. That's a good thing. And it also can tell you all the include paths. The dependencies show you what things you get as input. So in case of a routing service, taking as an example, it takes as input a routing engine. Okay, now I'm confused. So there's a top-level component that does the routing requesting. It talks to the service, that one talks to the routing engine, that one talks to a bunch of other things. Okay, so the routing engine is the thing that does the calculations, and the routing service is the thing that stores some data. Yeah, figured that out. Not because I figured it out because I looked at the code, just from the dependencies, I can see it does that. If I have a bottom-end component, it reads a file. What format is it? It has a dependency on tiny XML. I'm going to take my bets. This is going to be an XML thing. It can also tell you high level versus low level. So you have the high level routing request on top of the routing service, on top of the routing engine, on top of things below that. And it can tell you which things are at the top, which things have the most high level interface that you can think of, which things have the most low level interface. So for example, the SCL should typically be at the bottom, unless you're working on that. My application should be at the top. And there should never be a cycle between two components. Also, you can get numbers out of it, which management loves. So what's actually wrong with this cycle? Well, if I have two components, and they have a cycle between them, that means that if I'm using one component, I'm also using the other component. If I'm using the second component, I will also include the first component. So it's not actually two components, because if I depend on one of them, I get both. So it's not two components, it's one component. And you can repeat that trick with any other thing that's included cyclically. So that means that if I have a cyclic dependency tree that has a lot of nodes in it, that's actually not a split up bit of software, that's just one bit of code. And we can call that a monolith. So this is what you think of when you see a monolith. But this is not what a software monolith is actually like, because software monoliths don't have these nice defined edges, they don't have the single internal structure, they are not easy to understand. So let's take a different picture for that. It's more like this. It's like the Swiss Army component, but way more. You can do everything with this. You really should never want to use it. Does anybody have any of these? If somebody offers it to you, don't buy it. It's terrible. So we want to get rid of the cycles. So we analyze the cycles. We get all the cycles in the code base. We can find the shortest path from any component to any other component, just by asking for the components. And if there's a cycle, you can always get a path from A to B and back from B to A. It can also tell you there's no path from A to B. So I can tell in the build tool, I have routing and I have a completely separate component. These two should not be talking. So I can assert, if I run the dependency check from A to B and back, there's nothing coming out. I can check that. Not just at the actual level, but actually the implementation doesn't do that. I can ignore one file and see what does that do. Now, for an example, in the Clang code base, which I looked at with this, the Clang headers actually have this problem. In their basic set, they have one header file that is including a whole bunch of other components' header files. But if you ignore that one file, basically the entire problem disappears. You can look at that quite easily. You can just show that. And based on a request from someone who didn't seem to understand the implications of it being an exponential problem, cycles in a graph are an exponential amount of problems, he requested the ability to just take all the possible paths from my component back to itself and just list all of them. We'll just save it to a file, start on Monday, we start with the first one and solve that, and then we can go to the next one. So we ran that on our code base and crashed because it ran out of disk space. So I ran it, output redirected to gzip, to an extra hard disk that was completely empty. That was enough. It ended up being 300 gigabytes with 325 million possible ways of talking to yourself. So if I then think about my own software, what does it do? It calls into the things in the bottom, and then there's 325 million possible ways that I would need to check whether I'm calling into myself, whether I'm being re-entrant. I can't tell you what that component is going to do. I really don't want to tell you. So what else can you do? We have headers. We have headers that are being included in a lot of code. So there's a single header, you include that, it's 12 lines, and it has an include statement for some other header. Which one actually expands to the biggest amount of code? Because that one is going to cause a big slowdown. But not just that. If I have a header that expands to a reasonable amount of code that's included an awful lot of times, that might be the best place to start reducing that. Because as Bjorn mentioned in the keynote, the more you put into the compiler, the more time it's going to take to actually figure out what you're trying to say. And if you can get rid of them, that will save you time. It will just save you compile time, it will save you time in analyzing what things are for. The biggest one we found in our own code base resulted in 33,000 lines being included in 7,200 compilations. So if you're keeping count, that's 300 million lines of code being fed into the compiler. You can save some time there. It can tell you very large or very small files. It's a very obvious one. And so take all the information, put it in the CMake list, and this time we actually tried it. And it works, sort of, unless you do something weird. So for most components, you should be able to use this. It can also tell me the headers that I have but never include. I ran it on LOVM. I also looked at Clang, but I couldn't find anything. And LOVM seems to have, other than the examples, about 15 headers that they have but never actually include. So I suggest you take it, try it out, run it in LLVM and see what it does. You can also find a component that's never, and include statements are mapped to 2 headers. So going for the example with the engine, I have a component A, it has an engine. I have a component C, it has an engine, and they try to include it. Everything's fine. And now I'm working on component C. I need to use component A for some reason or other. So I add an include to it. I run all A's unit tests, everything is fine, I haven't modified it, I don't touch it. And component C doesn't build. Because I'm including the header from component A, and it's getting the wrong one. That's weird. So I can build component A, and it works, and I can include it, and then it doesn't work. Okay, the include path is wrong. Let's fix that. You need to go to the other one. It doesn't work. Because there's no possible way to make both of these include map to the right one, other than just giving them a different name. So given your include statement, you have to be able to say which header it's going to be. Otherwise, your build is unstable in this kind of way. So you can find these. You would also like your component to be coherent. This is a fairly difficult subject to grasp initially. If you look at these things, they're both made of parts. The part on the left, the puzzle, that one is coherent. If I'm using one part of this, I need to use all the other parts. They are interlinked, they work together, and they together form one function. If I look at the one on the right, if I'm using one book, I'm probably not needing any of the other books. And I'm really probably not using it. And this leads to a problem where if you have a component that is incoherent, you have a bunch of things that all these parts that you actually have in there need, that have dependencies, and you're pulling in all the dependencies for all of them, and not just for the part that you're trying to use. So that gives you false cycles, and one of the easy ways to fix them is just to take multiple parts and split it up. You also find a bunch of components that are overdependent. And overdependent means you're probably like a spider in a web. You have access to 100 components or more. There are people that are asking you questions for whatever service you're offering, and you call into way too many things. This basically means that that thing will be holding your code base together. Anybody calling into you will get all the dependencies beneath that. And you will basically be pulling everything together again. So this will keep your code base as one big blob, i.e. the monolith. So what you actually should be doing with a component is the same thing as with a class. If I have a class, people didn't know this like 30 years ago, you want encapsulation. You want to have the private members of your class to be hidden. And the only thing you want to expose is whatever you must expose so that people can use your class. So you have your own interface that you must expose, otherwise you can't use it. You have all the value types that you need to expose your functions. And you really shouldn't be exposing any implementation details. You don't want to tell anybody, hey, I'm the routing engine, I need logging, I need this, I need that, I need this. That means everybody's going to know your component. You will get a giant coding bottleneck in the place where you do that. People will be needing to update that all the time. So try to reduce that as much as you can. So we're using this at TomTom. We run it on every check-in. We detect the cycles. We try to find out if it's going up or down. If it's going up, there better be a good reason for that, and there are good reasons to make it go up. Same thing with unit testing. If you make the code coverage go down, you could just have removed the unused component with great test coverage. In this case, if you have a component that has cycles and you split it into two smaller components that are mutually independent but still part of a cycle, that's adding a component with a cycle. But it's still better. And the developers currently use it to auto-generate more than half the CMake files we have out of 1,400. So that means that all of those, assuming that the tool is working correctly, and as far as we can tell, so far it is, don't have any maintenance problems at all. They have no repetition anymore. They just repeat the thing that's in the source code automatically. There's no developer who can forget to update them. So all these dependencies are correct. All the other components, if they have dependency on something that you don't get automatically anymore because somebody removed their use, you're going to have to include it yourself. So all the other ones are most likely also correct. And we use it often for figuring out what problems there are, which headers we have that are not used, and so on. So feel free to come to our stand. We are also actively seeking people, C++ developers in Eindhoven, Berlin, Amsterdam, and Łódź, and we work on navigation devices and other devices. We also have sports devices. Thank you for listening. Do you have any questions? If so, please raise your hand.
Did you consider to ask the compiler to generate the includes?
Yes. The compiler is able to generate the includes that it's using right now, but given that your includes will need to be updated as you're adding and removing dependencies, the compiler will not be able to do that automatically. So you basically take the problem that you had and update it to the current state, which is useful, but every time you modify it, you're still modifying it by hand. And having it automatically is better than by hand.
Yeah, hello?
Yes?
So I just reading the screen, I get my answer. I was going to ask, do you share the tool you used? And is there some documentation? And is it limited to Clang and GCC, or can we use it on Windows with Visual C++, for example?
We have developed the tool internally over the past 2 years, and initially we made it run on Linux because that's what most developers use at TomTom. We had to port it, well, it's a funny story actually. We thought we had to port it to OS X because somebody wanted to use it on OS X, but the moment we wanted to start with that, somebody else told us, yeah, but it works already, it's been working for weeks. So it works on Clang and GCC out of the box, and for Windows we had a few modifications. Such that A, it works on Visual Studio, Especially the new Visual Studio, you do not no longer need to install Boost file system because it will use standard file system. But also Windows has a few quirks in that if you include a header with the wrong capitalization, there's no tool complaining about it. And if you check it with capitalization, like you would do on Linux and OS X, it's a problem because it will just not find it. So we also modified it to work correctly on Windows. So it will work on all three.
Okay, thanks. And I have an extra question.
Yes.
I've been working on exactly the same topic with my previous company, 4 million lines of code, custom tool. And the challenge we faced, we know we have legacy files with hundreds of lines of include files, just that. And it was, many of the includes were not necessary because it used to be necessary at one time, then you remove a function that was called and the include stays here. And this has proven to be very difficult to automate the detection of such things. Can you do this with your tool?
No, we cannot. But that's for a good reason. We didn't even try. If you have a file that has a lot of includes, those includes are necessary for a construct that is valid in C++. And you would need to parse the actual file to do that, which means that if we did that, it would be a lot slower. But there's already a tool that's very good at parsing C++ files and then telling you about it, which is your compiler, specifically Clang. There's already a project, I think 2 or 3 years old.
What you use. Yeah.
Exactly, which does that. And I would
but they will
recommend
write
either
completely, they do too much job actually. Wow. Okay. Thanks for sharing.
I would use that one, and if you don't think it works well enough, try to contribute to them. The same thing applies here, by the way. It's an open source project. We have approval from everybody to make it open source, so it is now an open source project. We are actively committed to maintaining it. If you have any requests, any issues, anything you want to fix in it, feel free to modify it yourself, or feel free to just make an issue out of it. Any other questions? Yes?
Your recommendation to use clean interfaces is, of course, variable and easily doable with pure virtual interface or whatever. But on the other hand, it means virtual function calls and so on, performance, lots of other talks tell you how bad this is. And is there any rescue to this catch 55?
It's a nice catch-22 indeed. You can make the code.
Yeah.
You can make your code abstract and have it all work with interfaces with all bunch of virtual function calls, and your cache is being trashed. You have a lot of overhead with that. Or you make it all statically typed, link everything together, but then it's basically impossible to make sure that everything works correctly. It's also a lot harder to test because you can't inject an interface. Compilers over the past 2 to 3 years have been working on link time optimization. This is the wrong conference for that. If you want to know more about that, go to LOVM.com last week. Sorry, I'm a bit late. Link time optimization basically allows a compiler to see I have a virtual interface and I have one class that it could be. Now, I don't know if there's going to be a plugin loaded later, so I cannot guarantee that it will go there. In 60% of the cases, I think the numbers were. In 1%, you do know because there's only one pointer that could end up there, but you didn't know it at compile time, you don't know it at link time. In 60% of cases, you probably know, but not for certain. So most compilers don't do anything with that, but the people at GCC have specifically added an optimization for that, that in the case that there's one option, and that's the majority, they take the function that it should be and just check is the vtable pointer this one, then we statically jump to that function instead of using the indirect invocation. So it doesn't wreck your cache anymore, it doesn't have a pipeline flush, and it doesn't have the majority of problems. And that gets rid of nearly all the slowdown you get from that. So use a new compiler. Did you test it on a recent enough GCC? I know that it's a recent optimization they have. I think it's an optimization that came out with 6. It's very recent, at least. Yes. Yes. So the first thing they do with devirtualization is the same that Visual Studio and Clang and LLVM also do, which is just a basic devirtualization. If there's one target and you know it, then remove the virtual function call. And GCC later on benchmarked it and figured out, well, they had a pie graph of how many targets there were for a virtual function call. And there was only one place where there was 1% where they knew exactly where it was going to go. There was 60% where they thought it was going to be one target, but they didn't know for sure. So that's when they added the actor optimization, which will be later than the initial check-in, but I haven't kept track of when exactly it was. So you would need to look it up and or try with a new GCC. Yes?
Just a question about the generation of the CMake list files. I'm not very used to CMake yet. I guess you do not insert header dependencies in CMake lists, but project dependencies. Is that right?
What do you mean with header dependencies?
As far as I know, you don't have to tell CMake which headers are needed for a CPP file. It can do it automatically, but the project dependencies are the thing you are generating here. Is that right?
Yes.
Okay.
The thing that you tell in CMake, the part that we can auto-generate, is given a project, which files are part of it. That's an easy one. Which other targets do you need to link to get your own headers to work? So which ones do need to be public so that my own headers can include the value types they need? Which ones need to be private so that I can link and build, but I don't need to expose to my customers? And also, given that somebody is depending on me, so that's the inverse relation, which file paths do I need to expose so that they can find the headers in my component with the include paths that they are using?
Thank you.
I also have a question. When you generate CMake files, when you include a private header, then this private include directory will appear in the CMake list files. Whereas when you handwrite your CMake list files, you will probably exclude it and get an error at compile time. Hey, you cannot include that file. So what make you decide for that approach?
That's a good question. Also, the reason why within TomTom we do auto-generate the CMake files, but we also force people to check them in still. As in, you could just integrate it into the build, run it just before CMake, let CMake run, and so on. That would work, but then you would have exactly this problem. Somebody adds a link to a component that you really shouldn't have, or uses an include path that's wrong, and you have no way of knowing it. So you are forced to regenerate, and if you regenerate it and you included somebody else's component with the wrong path, then their CMake file will be regenerated. You will have to actively decide, I am going to commit this into the control system, send it for review, and explain to them why I'm doing this.
Okay.
So that's more of the people approach to finding out how to prevent that rather than the technical approach. Okay.
Did you find any significant speed up or something with that? Like if you have cycles in the build and can be slow or build too many files or something like this?
The initial thing that we found was actually that the build slowed down a little bit.
Okay.
If we looked at the CMake file output, which was before we had the dependency checker, we had a script that took the output from CMake and used that to figure out which cycles it saw, and it found only 9. And then when we ran our own tool, it found about 130 in one big cycle. And if you actually specify that to CMake will be serializing the entire build of 130 components rather than just the 9 that we had before. So that causes it to slow down. But now we are seeing that it is increasing a lot in speed because many times when you're building some component test for your own component, you don't depend on any component from the cycle anymore because that component is now no longer part of it. So you only build the things below it instead of that thing plus the entire cycle plus everything beneath that. So in many cases, it's actually speeding up the build for the targets that you want to build.
But you still have cycles.
We still have some cycles. That's a question of priorities, rather. Any questions? Okay, thank you for your attention.